this video, we are going to solve a queuing network problem by hand. The network that we consider in this video consists of multiple external arrival processes and multiple MM1 and MMC systems, and also probabilistic routing and reentrant flows. But before we get to the problem description, I would like to mention that in related video modules, we have already introduced queuing theory and queuing systems and how they work. We have talked about the queuing formula for MM1 and MMC systems, and we've also talked about the assumptions of a Jackson network and how we can analyze a Jackson network. So my assumption here is that the viewer is already familiar with these topics. Otherwise, I would suggest that you stop this video, go and watch the related modules where we cover these items, and then come back and continue this video. So in this video, I will skip the introductory material and we'll go directly to solving a queuing network problem by hand. As you can see, we have 5 servers in this queuing network, servers A through E, and we have 2 sources of external arrivals into this network. So we have lambda 1 and lambda 2 as the 2 arrival rates that correspond to the 2 arrival processes that we have here. And we have probabilistic routings. So, for example, 25% of the parts that are processed on A will go to server B, and 75% will go to server C. We have our server information in this table. So we have the capacity of the server and the service rate of each server, denoted by mu, summarized in the table. So for example, for station A, we have a single server, and the server can process 150 parts per hour. And you can see the capacity and the service rate for the other servers on the table. So the arrivals are assumed to be Poisson, and our service times are also exponentially distributed. Both arrival and service rates are represented in the units of entity per hour. As you can see, the assumptions of this queuing network are in line with a Jackson network. So what we're going to do now is analyze the performance of this system by first analyzing individual servers and then aggregating our results. So we're going to start with our first server, which is server A. And our server is, as you can see by the data, it's an MM1 system. So we can simply use the formulas that are provided under the MM1 column in our table. So I'm going to calculate the utilization. So rho A is going to be a lambda A divided by its processing rate. So I'm going to have 115 per hour divided by 150 per hour. And this is going to give me a utilization of 0.77. So I'm going to do all my calculations to 2 decimal values. The next thing that we need to do is calculate the number in server A at steady state and the time that parts spend in server A at steady state. So I'm going to use these 2 formulas right here to do my calculations. So for LA, number in server A at steady state, I'm not going to rewrite the formula. I'm going to have 0.77 divided by 1 minus 0.77, and this is going to give me an expected number in station of 3.29, and for the time in station A, I'm going to have 1 minus 150 times 1 minus my utilization, which is my 0.77. And this is going to give me a time in station of 0.02, it's 29, so I'm going to put 3.03. Okay. And remember, since our arrival rate and processing rates are expressed in units per hour, we have our expected time in station A represented in hours. So we can go ahead and simply multiply this by 60 to get the time that entities spend in station A in minutes. And also please note that if you're getting slightly different values than what I get here, the reason is I'm not doing my calculations using the values that I round up to 2 decimals. I'm actually doing all my calculations using the exact values that I calculate in my Excel sheet. So the final values that I'm writing here are exact, and I'm not actually using the rounded values to do my calculations. So the next thing I would like to do is do my analysis for my next server, and for the next server I'm going to consider server C. I'm going to skip over server B because server B is a little bit more involved due to this feedback loop or reentrant flow that goes from D back to B, but we will discuss that shortly and learn how to analyze the reentrant flows into a server. So for server C, we have a capacity of 1, so we again have an MM1 system. So I'm not going to do all the calculations for an MM1 system. I'm assuming you guys can do it by yourself. So I'm just going to write down the final value. So I have calculated the performance metrics for my 3 servers, servers A, C, and E, which are my single server stations in my queuing network. Just before I continue, I would like to just make this note that for server C, the arrival rate, or lambda C, is going to be equal to the external arrival into the server, lambda 2, plus 75% of lambda 1, which is basically departures from server A. Similarly, for station E, lambda E, or arrivals into station E, is going to be 30% of the arrivals into station C. Okay, so the next step is to analyze stations B and E. So what I would like to do is start with server B. So we have an MM3 server here because it has 3 parallel servers, a capacity of 3. So for this server, what we need to do is to calculate the arrival rate. So we know that lambda C, or lambda B, is going to be equal to 0.25 lambda 1 plus 0.7 lambda C. And this value is going to be 185.13 per hour. But because of this reentrant flow that goes from station D back to station B, the effective arrival rate into station B is expected to be higher than this value that we just calculated. So let's see how we can go about calculating this effective arrival rate into the station. So I'm going to start with a simple example here. So let's say we have a station that has an arrival process of lambda 1, and some of the parts that are processed on this station will go back to the station with a probability of, let's say, 0.2. So basically 80% leave the station here. So the way we calculate the lambda effective for this station, which is expected to be greater than lambda 1 because of this reentrant flow that we have, is basically by using the this equation that we know input should be equal to the output. So our external input is lambda 1, and our output is basically 0.8 of this effective arrival rate into our station. So if we actually solve for our lambda effective, we will get basically lambda 1 divided by 0.8. So this is how we calculate lambda effective for a server when we have this reentrant flow back into the server. So in our case, for this for station B, what we have is station B, and then station D, and then we have this reentrant flow from D back to B, and we have an external arrival of 187.13 into station B. So this probability is 0.3, so 0.7 leaves station D. So the way we calculate lambda effective into B is basically using the same analogy. So lambda effective B should be greater than 187.113. And the equation we need to solve is 0.7 of lambda effective B, which is the output of this subsystem that we're considering here, should be equal to 187.13, which is the input into this system. So if we actually go ahead and do the calculations here, the effective arrival rate into station B is going to be equal to 267.32 per hour. Alright, so now that we have calculated the effective arrival rate into station B, we can use the MMC formulas to evaluate the performance of this server at steady state. So what I'm going to do is first calculate the utilization of this server. So the utilization rho B is going to be equal to lambda effective B divided by, since we have 3 servers in the formula for the utilization, we have C times mu B in the denominator. So I'm going to have 267.32 divided by C is 3 times our service rate for station B, which is 120. And this is going to give me a utilization of 74%. Now that I have the utilization, the only thing that I need to calculate in order to be able to use these formulas is this value of P0 that appears in 2 of the formulas that we need to calculate. So P0 is basically the probability of having 0 entities in the system at steady state. Let me just go through the calculations, and you will see that it's not actually as complicated as it looks. So what I'm going to do is that I'm going to calculate P0 for station B. So I'm going to start with the first expression. So in the first expression, I have C, which is 3, times rho, which is 0.74, to the power of 3. In the denominator, I have 3 factorial, which will be 6 times 1 minus utilization, 0.74. So that's my first term. This second term that I have here is basically summation. So in this summation, the variable n starts at 0 and goes up to c minus 1, which in our case is 2. C is 3, so we start from n equal to 0 to n equal to 2. If I substitute n as 0, anything to the power of 0 will be 1, and 0 factorial is also 1. So my first term in the summation is going to be 1. The second term is going to be c, which is 3, times my utilization, 0.74. N is now 1, and in the denominator, I have 1 factorial, which is 1. The next term, now n is 2, so I have c, which is 3, times my utilization, 0.74, this time to the power of 2. And in the denominator, I have 2 factorial, so I will have 2 here. Sorry about that. 2. And the whole expression that I've just written here to the power of negative 1. So if I actually go ahead and do the calculations, what I have is the first term will be equal to 7.01 plus 1. This term is going to be 2.22, and the last term will be equal to 2.48 to the power of negative 1, and if you do the math, you will end up with 0.08. So this is the probability of having 0 entities at this server at steady state. So now the rest of the calculations will just be a practice of substituting the values into these formulas. And if you actually do the math, this is what you get. So for the L, B, what I'm getting is 3.83. And for WB, what I'm getting is 0.01 hours. And finally, I will leave the calculations for station D to you guys as an assignment.